This is our lecture video to get us introduced to the qualitative analysis scheme, sometimes called the Qual scheme. So we're going to look at some of the common cations of the elements to separate. So we'll separate out the group 1, which are silver, mercury, and lead, the group 2, the group 3, the group 4, and the group 5. So we'll just look at what these different groups mean in the upcoming slides. So first we want to look at some definitions just to get you started. Coordination compounds, metal complexes, or just complexes are compounds that contain a central metal atom or ion, usually a metal surrounded by a cluster of ions or molecules. A complex is a central metal ion surrounded by a set of ligands. So an example would be nickel tetracarbonyl. So here we have the nickel center surrounded by 4 carbonyl ligands, or this cobalt hexamine complex. So we have the cobalt with 6 amines coordinated to it, and it has a 3+ charge. So both of those are examples of complexes. One happens to be neutral and the other happens to have a charge associated with it. Ligands are an ion or molecule that can have an independent existence. They use lone pairs to bind to the metal, and they are Lewis bases. So in our example here of the nickel tetracarbonyl complex and the cobalt hexamine complex, the carbonyl is the ligand and the ammonia is the ligand. And the coordination compound is either a neutral complex or an ionic compound in which at least one of the ions is a complex. So for our examples, the nickel tetracarbonyl is a coordination compound, and then the cobalt hexamine chloride is a coordination compound. So notice that here we have the cobalt complex. So the complex is what's in the brackets. So everything that's in the brackets tell you what's attached to the metal. And then the chlorides here are just simply balancing out the charge. So there are 3 chlorides to balance out the 3+ charge for the cobalt complex. And remember, each ammonia is neutral, so it has no charge. So if the ammonia is neutral and the overall charge is 3+, then the oxidation state of the cobalt has to be 3+ as well. Now the coordination number, that's the number of atoms that are bonded to the central metal atom or ion. So if we're looking at the nickel tetracarbonyl complex, the coordination number is 4 because there are 4 carbons bound to the nickel. And then the cobalt hexamine complex, the coordination number is 6 because there are 6 ammonia molecules attached to the cobalt. So in the qualitative analysis, basically what we're going to do is we're going to start to separate ions out in groups. And once we separate the ions out in groups, then we can do specific tests and other separations to identify particularly which ions that we actually have in solution. The first group is the group 1, and we call these the acid insoluble chlorides. And in this group we'll be able to precipitate out silver, mercury, and lead. The group 2 ions are ions that don't precipitate in group 1 but have acid insoluble sulfides. So the sulfide, so that S2-, so sulfide is an S2-, that will bind to those metals. So it will form things like the lead sulfide, the copper sulfide, the bismuth sulfide, and the tin sulfide, the mercury sulfide, the antimony sulfide, and the tin sulfide. Now we are going to supply the sulfide in the form of hydrogen sulfide, so H2S, but that has an equilibrium that it will establish. So it'll produce 2 protons and sulfide ions. If we push the equilibrium to the right by adding a base, so the base will consume the protons, the proton concentration will go down, and by Le Chatelier's principle, the reaction will shift to the right to increase the concentration of the sulfide. So if we have an excess of sulfide ions, then the group 2b, so this is a subset of the group 2 ions, these will form anionic sulfide complexes. So they'll actually bind more sulfurs and form a new complex. For example, the mercury sulfide will then bind another sulfur to have 2 sulfurs, so this is mercury disulfide, and it has a 2- charge. And once you form these anionic sulfide complexes, these all have charges compared to the neutral species. So because these are charged, they're going to dissolve better in water, so these will become soluble. Whereas if it's not charged, it will be insoluble. But the group 2 ions, they precipitate out with low concentrations of the sulfide, and you can separate these out into two subgroups, whereas the first one doesn't form a new complex with excess sulfide, and the group 2 does form a new complex with extra sulfide around. Now the group 3 ions, these are ions that don't precipitate in group 1 and 2 but have basic insoluble sulfides. So in the first set of conditions with the hydrogen sulfide in the group 2, so we had that equilibrium of the hydrogen sulfide breaking up into the H plus, or sorry, 2 H pluses and 1 sulfide. Under acidic conditions, so the group 2 are under acid conditions, the pH is low, so that means a high H plus concentration. So with a high H plus concentration, that pushes this equilibrium to the left. So that means the sulfide concentration is low. But in the group 2, we're going to change the pH of the solution. So we've still got the hydrogen sulfide in solution. And we are going to increase the pH. And when we increase the pH, we're adding more hydroxide ions. Those hydroxide ions combine with the protons, which cause the concentration of the proton to go down. So if that concentration goes down, the equilibrium shifts to the right to make up for this loss, and that's going to cause the sulfide 2 plus, or sorry, the sulfide 2 minus concentration to increase. So for the group 3 ions, you have a larger sulfide concentration than for the group 2 ions. And in this case, when you have the higher concentration of the sulfide, the iron, the zinc, and the cobalt and the nickel complexes precipitate out as the sulfide, and so does the manganese precipitate out as manganese sulfide. But because you've added base, you've also added more hydroxides, and so in this case, the aluminum and the chromium will precipitate out as hydroxide species. So aluminum hydroxide and chromium hydroxide. Now the group 4 ions, those don't precipitate out in groups 1, 2, and 3, but they have basic insoluble carbonates. So you can have a basic solution with carbonate ions in there, and that's going to cause the barium to precipitate out as barium carbonate, the calcium carbonate to precipitate out, and any strontium will precipitate out as strontium carbonate as well. And then lastly, the group 5, if nothing precipitated out in the group 1, 2, 3, or 4, that leaves your group 5 ions, and those are soluble in basic carbonate solutions. And your group 5 ions are going to be sodium, potassium, magnesium, and ammonium. Okay, so just kind of a breakthrough of what's going on. So each time you do a group separation, you are removing a group ion. So, and when you're removing it as a solid, and the solution or the filtrate, the liquid, is left behind. So let's say you have an unknown and it contains some group 1, 2, 3, 4, or 5 ions. So once you do your group 1 test, if you get any solid out, you have a group 1 ions. And so those are precipitated out as the acid insoluble chlorides. So if you remove the group 1 ions as a solid, what's left in the liquid are either group 2, 3, 4, or 5 ions. Then your next sequence of events is to remove the group 2 ions. So those are removed as solids as well, the acid insoluble sulfides. So you're adding hydrogen sulfide in an acidic form, and so the group 2 ions will precipitate out, and you can remove the liquid from the solid. So in the liquid you'll have the group 3, 4, or 5 ions, and we also call that liquid the filtrate. We then remove the group 3 ions as a solid by adding base to increase the sulfide concentration. And so we get the basic insoluble sulfides and hydroxides to precipitate out. And in the filtrate, that will leave us our group 4 and 5 ions. And then lastly, we do our group 4 separation, And in the group 4, you'll have these solids that are removed, and that leaves behind the group 5 ions that are left in solution. So to remove things out, you're precipitating them out, and you decant off the liquid, or you remove the liquid and leave the solids behind, and you continue on with your test. So I just want to kind of look at the precipitation of the group 1 ions. Remember, we said those are the acid-insoluble chlorides. So notice here, these are the KSP, so the solubility constants, those equilibrium constants, for the mercury, the lead, and the silver complex. So the mercury, the silver, and the lead complexes. And notice how these are very small KSPs. So this means they're very poorly soluble. So if you add chloride to the silver that's dissolved, or the mercury ion that's dissolved, they will precipitate out. And the same thing will happen with the lead. So if you add chloride to the lead 2+ ion, you'll precipitate out the lead chloride ion. But one of the things I want to draw your attention to is notice that the formation constant for the lead complex is a lot larger than that for the silver chloride and the mercury chloride. So it means that the lead is slightly more soluble in water than the silver and the mercury complex. So if you actually heat the lead chloride solution, you can actually get the lead chloride solid to dissolve, because at the higher temperature it becomes more soluble. And it's also because of this larger KSP value that sometimes separating out the lead from the other group 2 and 3 and 4 and 5 ions isn't always clean, because it does have some solubility in it. So we'll look at that again later on. But these are the reactions for the group 1 ions. Now in the group 2 ions, we're going to decompose thioacetamide. So this compound right here is the thioacetamide. And when it decomposes, it'll give you the acetate ion, ammonium, and hydrogen sulfide. And this is one of the equations that people oftentimes forget to write down as one of the equations in their practical, because you'll use this equation for the group 2 ions, but you'll also use it for the group 3 ions as well. But it's this decomposition of the thioacetamide that gives us the hydrogen sulfide. And the hydrogen sulfide establishes an equilibrium, because this is an acid, so it produces 2 protons and the sulfide ion. So hydrochloric acid furnishes hydrogen ions, which represses the ionization of hydrogen sulfide, and this causes a decrease in the sulfide ion concentration of the solution. So what we're doing here for the group 2 ions, we have hydrochloric acid, so we increase the H+ concentration, so that pushes the equilibrium to the left, and so that's going to lower the concentration of the sulfide. So we have low sulfide concentration when we increase the acidity of the solution by decreasing the pH, by adding more protons to it. So these are the reactions of the group 2 ions as they react with the hydrogen sulfide. And notice that each of the equations, that everything is completely balanced, including the charges. And remember, when we talked about earlier, the group 2 ions can be separated into 2 subgroups, 2A and 2B. The separation of the group 2 ions into 2 subdivisions is based on the fact that mercury sulfide, antimony sulfide, tin sulfide form soluble complex sulfides in alkaline sulfide solutions, whereas the lead sulfide, the bismuth sulfide, the copper sulfide, and the cadmium sulfide do not form these complex ions. The reagent used in this separation is sodium sulfide, which is made by the action of hydrogen sulfide formed by the hydrolysis of the thioacetamide upon sodium hydroxide. So basically what we're doing is we have the equilibrium of the hydrogen sulfide. So we have the hydrogen sulfide breaking up into the H+ and the sulfide, but we're adding the hydroxide, and the hydroxide neutralizes the H+ to form water. So as we increase the base concentration, that pushes the equilibrium to the right, and that's going to increase the sulfide concentration. So we have high sulfide concentration at high pH. So when you increase the sulfide concentration, these sulfide complexes can then bind additional sulfides to make these anionic sulfide complexes. Now the arsenite complexes, we won't be using them in our Qual scheme. Now the group 3 ions, these precipitate out in basic sulfide conditions. So analytical group 3 contains the metallic ions nickel, cobalt, manganese, iron, aluminum, chromium, and zinc. These ions are not precipitated by hydrochloric acids of the group 1 test, nor are they precipitated by sulfide ions in solutions that are 0.3 molar in hydrogen ion. The concentration of sulfide ions in the 0.3 molar hydrogen ion solution of the group 2 precipitation is too small to allow the solubility products of the group 3 sulfides to be exceeded. So the hydrogen sulfide in an aqueous solution of ammonia has a much higher sulfide ion concentration due to the formation of ammonium sulfide according to this equation here. So we're adding the base and we're increasing the sulfide concentration. The base will consume the protons from the acid, and so that pushes the equilibrium to the right when we increase the concentration of the base. The resultant sulfide ion concentration is sufficiently large so that the solubility product constants of these sulfides of cobalt, nickel, manganese, iron, and zinc are exceeded and the precipitation occurs. Likewise, the hydroxyl ion concentrations of the ammonium sulfide solution is great enough to precipitate the hydroxides of aluminum and chromium. The solubility products of aluminum and chromium hydroxides are lower than those of the corresponding sulfides, and thus favoring the precipitation of the hydroxides. So hydrogen sulfide is produced upon the precipitation of this group by the acidic hydrolysis of thioacetamide, and upon the addition of aqueous ammonia, the following precipitations occur. So as the cobalt binds the sulfide, you get either a brown or black color. The nickel and sulfur produces a brown or black color. The manganese and sulfide produce a light pink. The iron sulfide produces black, the zinc sulfide white, the aluminum hydroxide white, and the chromium hydroxide is blue-green. Now this will give you a bit of a hint when it comes to the practical, because in the practical you're only going to have one group 3 ion. So if you start to see one of these colors, this will help give you an indication of what ion that you have in there. Now when you're doing the practice for the lab practical, you will have 2 group 3 ions in there. So you have to be careful. So you may have a light pink and a little bit of white mixed together. So it may be more difficult to distinguish what you have there, but this is a good indication of what ions you may test positive for later on when you do your positive test. Now in the event that iron is present in the original solution in the 3+ oxidation state, it will be reduced by the hydrogen sulfide in acidic conditions to form the iron 2+. So the iron 3+ gets reduced by the hydrogen sulfide to form iron 2+ if there's any iron 3+ in solution. Now let's look at the group 4 ions. Analytical group 4 contains bimetallic ions barium 2+, strontium 2+, and calcium 2+. These metals form chlorides, sulfides, and hydroxides that are soluble under the conditions that prevail in the precipitation of the group 1 and the 2 and the 3 ions. The carbonates of barium, strontium, and calcium precipitate in aqueous ammonia solutions containing ammonium carbonate. The concentration of the carbonate ion in a solution of ammonium carbonate is too low to affect a complete precipitation of barium, strontium, and calcium due to the partial hydrolysis of the carbonate ion. So this is the partial hydrolysis of the carbonate ion. So carbonate reacts with water to form the bicarbonate and the hydroxide. This hydrolysis is repressed by increasing the hydroxide concentration. So you increase the concentration of the hydroxide, which pushes the equilibrium to the left, and it's going to increase the concentration of the carbonate. So the hydrolysis is repressed by increasing the hydroxide ion concentration of the solution, the additional hydroxide ions being supplied by the buffer pair aqueous ammonium and ammonium chloride. These conditions permit a carbonate concentration high enough to precipitate barium carbonate, strontium carbonate, and calcium carbonate, but not high enough for magnesium carbonate. At the same time, the hydroxide ion concentration in this buffered solution is not high enough to precipitate magnesium hydroxide. So this is just a flow chart to kind of see how we start to separate everything, kind of give you another visual as to what's going on. So I know there are a lot of different parts and pieces to this Qual scheme. So you have the possible ions that could be in there. In reality, we're only going to be doing the group 1, the group 3, and the group 4 ions. But it's important to know what's going on in the group 2 as well, because you'll be asked questions in your Introduction to the Qual Scheme lab experiment. So first you do the group 1 separation, so GS just stands for group separation. That's group separation 1, where you're removing the acid-insoluble chlorides. So the acid-insoluble chlorides will come out as a precipitate, so that's either silver, mercury, or lead. And you're going to heat to dissolve the lead complex, and with the liquid, the filtrate, you'll do a specific test. So ST is a specific test. So this is a specific test for lead. If it turns yellow, you have lead. And notice the way I've got my flow chart set up, that my filtrates are always going to the right and my precipitates or my solids are always going to the left. So after I heat to dissolve the lead complex from these ions, if I get a solid that's still left behind, I'll do my specific test 2 to test for mercury. And from the filtrate from that test, I'll do a specific test 3 for silver. And if I get a white precipitate, that tells me I have silver. So from the filtrate that I saved from the group 1 separation, this is where I have either a group 2, 3, 4, or 5 ion. So my group 2 ions, I will precipitate out, and then I'll separate them out into their 2 groups. And remember the GS2B, this is where we increase the sulfide concentration by adding a base. The sulfide concentration increases, and these form the anionic sulfide complexes. Now I'm going to go back up here to the group 2 separation. Remember the solid we used to do the test for the specific test for the group 2 ions, but the liquid that was left over, that filtrate, had to be saved because you could still have group 3, 4, or 5 ions in that filtrate. So using that filtrate, we then perform the group 3 separation. And if there's any cobalt, nickel, iron, manganese, aluminum, chromium, or zinc, it will precipitate out. And the filtrate, the liquid, is saved for the group 4 separation. Now, in the group separation of 3, we can divide these out into group 3A. So group 3A contains nickel and cobalt. And you'll do your test for nickel and cobalt. And then your group 3B ions, so the iron, the manganese, aluminum, chromium, and zinc, you'll separate these out, and you'll do the specific test for each one of those. And then your filtrate from the group 3 separation you'll use to do your group 4 separation, and you'll save the filtrate for group 5, but in reality in lab we're not going to be doing the group 5 ions, so that filtrate you can throw away, but the precipitate may have barium, calcium, or strontium in it. So you're going to dissolve, and then you're going to separate that solution into 2 test tubes. One sample is going to be used for a specific test 18, and the other is going to be used for a specific test 15, 16, and 17. So these flow charts are just showing you how you start to separate the different ions. After you've separated them, you do a specific test to confirm, based upon the results that you see, whether or not you have that ion in solution. And the group 4 separation, you're going to do an extra test for it. You're going to do flame tests. So you'll do some chemical tests to see what happens, but you'll also use a flame test to confirm what's going on. So I just want to show you how your lab practical will be scored. 30 points will be the accuracy of how you identify your unknowns. Now anytime you think you have one of your ions identified, you may go up to your lab instructor and ask them if you're correct. So let's say you get a solid precipitate out for your group 1 separation and you get a yellow precipitate when you do the test for lead, then you can go up to your instructor and say, do I have a group 1 of lead? And if you're correct, you'll get full credit. If you don't get it correct the first time, then you can do a second attempt, and if you get a second attempt, you get 8 points for it if you get it right. And if you don't get it right on the third attempt, you get 0 points. But I highly suggest, once you are sure that you know what your ions are, ask your instructor if you have it right. That way you can make sure that you have the correct equations happening. And you can figure out what you need to do to correct a mistake if you don't have it right. Because too many times students will wait to the very end where they only have 30 minutes left of the practical and they find out something went wrong because they don't know what their ions are. Then they end up losing all of their points because, let's say, you wait to the last and you say you have silver in here and silver isn't your ion and that's your only attempt that you make. Then you lose all of your points if you only make one attempt and it's wrong. You'll also have 15 points associated with safety and technique. So if you have no incidents of poor technique noted, then you'll get all of your points. Now, if you have a safety violation, that counts as 2 technique errors. And a safety technique or a safety violation could be anything such as not wearing goggles, pointing a heating test tube towards someone else, opening a spinning centrifuge, or something like that. Now you will be asked to correct your safety violation, but you'll also lose points for that safety violation as well. Then 55 points is associated with your write-up. And 15 of that 50 is your flowchart, and then the equations and the clarity and detail of your write-up. So we're looking at the flowchart first. So we have 4 different categories: the exemplary, good, inadequate, and poor, and these are the points associated with that. An exemplary flowchart, it's neat. It shows how decisions were made as to which test to do and in which order, and it doesn't list things that were not done. The results of the test are clear and identified. Ions are clearly labeled. Test names and group separation names are clearly labeled. And then extraneous information such as procedural details are not given. And what this means is that it should not look like the procedural flowchart given in the lab manual. So if you do all of these things, you'll get your full 15 points associated with the flowchart. So this is just to give you an idea of what your flowchart would look like. So this student had nickel and mercury as their ions. So notice they have their possible ions at the top. They did a group 1 separation. They saved their filtrate and they took the precipitate and they knew that they had either silver, mercury, or lead. They heated to dissolve the complex, and so they separated out the filtrate. And when they did the specific test for lead, they didn't get a yellow precipitate, so there's not lead in there. But when they took the precipitate from the heating and they did the specific test too, they got a black or gray precipitate. And so they've circled this here, and they let me know that clearly that mercury is in the solution, or is in their unknown sample. And they've gone through the group 3 separation. They did the group 3A, then they got their precipitate. They got either cobalt or nickel. They did the specific test 10, and it wasn't a yellow precipitate, so there's no cobalt. And they did specific test 9. They got a cherry red precipitate, so they do have nickel. And notice that they don't have from the filtrate, they don't have any information for the group 4 separation, because there was no need to do the group 4 separation because they got a precipitate for the group 1 and they got a precipitate for the group 3. So they don't list any extraneous information or things that were not done, only the things that were done. So in the practical, you also have to remember that you'll be given either a group 1 and a group 3 ion. So in this case, this person had a group 1 and a group 3, or you'll have a group 3 and a group 4. If you have a group 3 and a group 4, you won't have a precipitate, so you won't need to show anything associated with a group 1 separation if you have a group 3 and a group 4. And then 20 points are associated with the correct equations. So to get all of your 20 points, the equations are balanced, including charges, and the states are clearly indicated, so whether they're aqueous or in the solid state. The equations are clearly labeled to show in which test or separation the reaction occurred. All chemical reactions are represented with an equation. So if there is a chemical reaction that takes place, you have to write the equation associated with it. And this includes the specific test and the group separation test. So any chemical reaction that takes place, you need a chemical equation that says what that reaction is. And then other chemical equations such as the generation of sulfide from thioacetamide are also shown. So that's what we're looking for when we're looking at grading the equations sections of your lab practical. And then 20 points are associated with the clarity and detail of your write-up. So the layout follows the guidelines exactly, and we'll show you what those guidelines are. It's neat. The reader can easily follow what happened. Any errors are crossed out with a single line through it. The test and separations are clearly labeled. The handwriting is easy to read. Conclusions are logical. Details are succinct, yet enough detail is given to understand what's going on. And the write-up honestly depicts what happened. So don't tell me what was supposed to happen or what you thought was supposed to happen. You need to actually show what actually did happen. So this is how your write-up should look like. There should be a title for the test that you're doing. So in this one, the student wrote, this is a group 1 separation, and the title of that test is the acid insoluble sulfide. The student listed the reagents that were used. So they used the 6 molar hydrochloric acid. Then in the procedure section, they listed exactly what they did. So somebody that's reading this could follow along as to what happened, and they could repeat what the student did. The student took 1 ml of the unknown sample and added to the test tube. They added 3 drops of 6 molar. Should have only added 2 drops, but an extra drop leaked. So those little pieces of information are helpful if something goes wrong to help your instructor figure out what to do next. So this is just exactly what was done to the sample. And after the procedure, you're going to list any observations. So after this test, a white precipitate was formed, and the conclusion was that there's either silver, mercury, or lead that's present. Now, as you're doing this write-up, you'll leave a blank spot for the equation. So put your equations here and leave this blank. Then once you do your test and you figure out exactly which ions are there, go back and write the equations for only the things that were there. So once you later on and you do the specific test for silver and you know that silver is your ion in there, go back and write the equation for silver, because we only want to see the equation of what actually happened. And don't forget to leave space for this as you're going along and writing down what you did, because this equation needs to be associated with a group 1 separation. And then after they did the group 1 separation, then they did the specific test 1 for lead. So the reagents were potassium chromate. You want to list your procedure. Again, list everything that you did, your observation. So there was still a white precipitate after heating, and there was no yellow precipitate formed. So since there is no precipitate formed and you still have a white precipitate, that tells me that there are no lead ions present in the unknown. So since no chemical reaction took place, then no reaction. So the equation is no reaction, thus no equation is needed. So remember, for your equations, be sure to give the balanced chemical equation for every reaction that occurred in this test. Be sure to include the states in your balanced equation. Write the balanced equations after you determine the identity of your unknown. And be sure to leave adequate space. Giving equations for reactions that do not occur in your test will result in a severe point of penalty. And if no reaction occurred, then write no reaction, thus no equation needed. And that's what this student did here for this lead test. So here are some practical instructions and reminders. You're going to pick up the yellow sheet with your name on it, and this is where you're going to record your data on. Locate your sample number with a number on your yellow sheet and grab that number unknown only. Taking another test tube is a 0 on the practical, because you'll be assigned a specific unknown sample associated with your yellow sheet. And if you take another sample solution, you're going to get the wrong test for the ions that were assigned to you, and your instructor will have a grading sheet that lists what ions that were assigned to you. Do not talk to anyone, pass notes, nor share equipment. Doing any of these will result in you failing the practical and possibly the course, because this would be considered cheating. So remember that lab practical is actually a test. You're not allowed to work with anybody. But however, you can share a Bunsen burner and or a hot water bath, simply because there's just not enough space and things get a little crowded. You may have anything you want written in your lab book, but you cannot have any added sheets or loose sheets of paper in your lab manual. You must finish each day by the scheduled end of class, and there are no time extensions. On the first day of the practical, you must turn in your yellow sheet of observations before you leave class, and they must have your notes on them or you will lose points. Because remember, your yellow sheet, that's basically your lab notebook, and you have to take the notes as you're going along. You can't just write them somewhere else and then transfer your notes. You have to write them in your lab book as you're going along. And you cannot take those with you. Those have to remain in lab with your instructor. They will be returned to you the next lab period. If you need to leave the classroom during the exam to go to the bathroom or the stockroom, only one person at a time may be gone, so you need to tell your instructor when you leave. For the lab practical, you will have 2 metal ions in your unknown sample, either a 1 and a 3, or a group 3 and a group 4 ion. This is important to remember because your instructor cannot tell you this during the lab practical. You may check if your determination of your unknown is correct at any time, but each incorrect answer will be a deduction from your exam grade. Start your water bath right away so that it can be heating while you do other things, because heating the water and getting it up to the right temperature can take a while. So you want to get that started going first so that it's ready to go when you need it. You may want to bring Sharpies to write on your test tubes and a lighter so that you do not have to hunt down matches. This will just save you some time. And also it's easy because you'll be working with different samples to get your samples confused. So having a Sharpie to write on them and label the test tubes will make it easier to make sure you have the right test tube. Add only 3 or 5 boiling chips to your hot water bath so that your test tubes don't rattle around so much in the water, because there's rattling around and the test tube bumping up and down will cause cracks and eventual breakage of your test tube. Make sure you follow all safety rules, so no shorts, hair must be pulled back, goggles on, wear gloves, etc. Do not hoard or hide reagents, so get what you need in the back and then promptly return them. Return the bottles to the back shelf in alphabetical order. Close the caps. Failure to do so will result in a point deduction. Sit in your normal spot near your lab drawer, so this makes it easier to find you and we know what mess or clean area goes with what student. Also be sure don't overfill the waste container. Doing so will cost you points. When you're finished at the end of the day, make sure you wipe down your lab bench before you leave, and it should pass the white glove test. Because remember, a lot of these compounds that we're working with are carcinogens, and they're actually very dangerous and toxic. So we want to make sure we don't contaminate the area. We want to make sure it's nice and clean for the next person that comes in. And you may want to have a personal waste bottle, and this will save you time running back and forth to the waste bottle. So if you have a little beaker or Erlenmeyer at your desk and it's labeled waste, you can pour all of your waste in there, and then at the end of the day you can dump your waste. Also, don't let your tongs contaminate your solution. So notice here we have a picture of the tongs holding this evaporating dish, and it's heating up the solution inside and it's evaporating some of the liquid. Remember, these tongs are composed of iron and they sometimes rust and things like that. If any of the rust or the other compounds are on the tongs touch your sample, you can contaminate your sample and you may get a false positive test for one of the ions. So don't let your tongs touch or contaminate your solutions when you grab things with them. Also, you need to make sure you make notes as you go along, record your procedure and your observations. Create a flowchart that shows how you determined your known. And do not include things that you did not do. Neatness counts. And don't do a flowchart like the one in your lab manual. Create a simplified version as instructed by your lab instructor. For each test that you do, create a summary such as the one on your report sheet. Show balanced chemical equations for all metal ions present in your sample, and do not forget to show states. Do the equations last because you need to first conclude which metal ions you have in your unknown. And this will make your equations much less complicated, because remember, neatness counts. You may also want to prepare for accidents. So you may want to prepare a duplicate sample in case the test tube breaks, but be careful to watch the clock. So for example, the group 3 separation is a bit time consuming. So you may want to do 2 preps of the group 2 or the group 3 separation at the same time, because they do take a long time, and doing 2 at the same time is less time intensive than doing them sequentially. So doing 2 at the same time, it's just kind of your insurance policy. You can choose not to do this, but I've seen it save students a lot of time if they prepare an extra sample. Also, remember, be careful that the corks are dirty and absorb solutions. So don't invert your sample or allow your sample to come in contact with the corks, because this may contaminate your sample. And when you get your unknown sample, be sure to thoroughly mix the sample so that you have a homogeneous mixture of your ions. Because the way the stockroom makes up your unknown samples, they come by with squirt bottles and just squirt things in, but they don't necessarily mix the solution. So you may have layers in your test tube that you cannot see. So make sure to stir or mix the sample thoroughly and then take your aliquot out. Also, be careful about walking away from centrifuges. You need to stay there beside them, because sometimes they walk and will wobble off the table. The reagents are alphabetical in the back. Put them back where they belong. Do not keep them at your bench top or you'll lose points. Also, remember, cold glassware looks the same as hot glassware. And I say this just so that you remind yourself to be careful when you heat things up and you don't accidentally burn yourself by touching hot glassware. You must use either blue or black ink to record your data. Remember, no pencil, because we're recording our data in our lab notebook. And when you take a sample of your unknown, be sure to make sure that the sample is well mixed before you take an aliquot. So this is what I was mentioning before. Make sure your unknown sample is well mixed so that you have an even distribution when you take out your sample. So that concludes our introduction and our overview of the Qual scheme.